Good morning. Today we are going to present the paper Economic Analysis and Optimization of a Biomass Integrated Gasification Combined Cycle based on externally fired gas turbine, steam Rankine cycle, organic Rankine cycle, and absorption refrigeration cycle. We are going to analyze 4 sections: introduction, methodology, results, and conclusion. Let's start with the introduction. The global energy demand is projected to increase by around 37% by 2035, with fossil fuels still providing about the 80% of the total supply. This dependence leads to environmental challenges and motivates the search for cleaner technology. One promising option is the Biomass Integrated Gasification Combined Cycle, or BIGCC, which converts biomass into syngas containing carbon monoxide, hydrogen, and carbon dioxide. However, conventional gas turbines require expensive cleaning of the syngas due to its low heating value. The externally fired gas turbine, or EFGT, addresses this by heating clean compressed air through a heat exchanger, preventing direct turbine contact with the syngas. Additionally, waste heat can be recovered using the steam Rankine cycle, or SRC, the organic Rankine cycle, ORC, and the absorption refrigeration cycle, ARC, which boosts efficiency and enables combined cooling and power generation, known as CCP. Despite advantages, the configuration has not been fully explored. This paper aims to model and optimize such a system to maximize exergy efficiency while minimizing the levelized cost of electricity. Now let's check the methodology. This combines thermodynamic model with the exergoeconomic evaluation for a combined cooling and power system, integrating an externally fired gas turbine, a steam Rankine cycle, organic Rankine cycle, and absorption refrigeration cycle. The chemical exergy of biomass is calculated from its lower heating value, multiplying by a coefficient, which depends on the mass fractions of carbon, hydrogen, and oxygen in the fuel. This coefficient corrects the elemental composition and allows for a more accurate estimation of the biomass chemical exergy. The general exergy balance considers the exergy of fuel as the sum of the product exergy, the destroyed exergy, and any losses. The analysis disregards kinetic and potential exergies, focusing on physical and chemical components. For the exergoeconomic part, the specific exergy costing, or SPECO, method is used. This involves a cost balance for each component, where the sum of input exergy cost, heat interaction cost, and the capital plus operation and maintenance cost equal the output exergy cost. The methodology delivers key indicators such as component-wise exergy efficiency, the unit cost of exergy, and a breakdown of where costs and irreversibilities are concentrated in the system. Here we can see Table 1 that presents the detailed mass and exergy balance equation for each major components in the system. For example, in the condenser, the heat transfer rate is calculated from the product of the mass flow rate and the enthalpy drop between inlet and outlet, ensuring conservation of energy within the control volume. Similar formulations are applied to the other components, adjusted to their functions, whether they are producing work, like the vapor turbine and pumps, or the exchanging heat, like the evaporator and IHE.
I thought about the result of the exergoeconomic analysis. The result where we had the table 2. This table shows the exergy balance performance on each of the combined cycle equipment. This balancing where exergy of the first exergy of the product, and the exergy the extrusion. The table 3 we have, or this table shows the respective cost balances and the auxiliary equation for each of the system equipment. And the table 4, this table shows the property of each of the string of the combined cycle. These properties were temperature, pressure, mass flow, entropy, exergy, and cost rate. We had two cost rate. We had the uh, dollars per hour and dollars per gigajoule. And the table 5, this table details the distribution of the thermoeconomic parameters across the system components. We have the exergy of the free, exergy of the product, and the exergy of the extrusion. These units were kilowatts. And also we have the efficiency exergy. And we have the cost rates, and we have the factor F and the factor R. The factor F was the exergo-economic factor, and the factor R, this was the relative cost difference. And the figure 1, we have the Sankey diagrams of the exergy flows. This figure shows the Sankey diagram where the biomass combustion chamber is the main contributor of the total exergy destroyed of the system. And the figure 2, we have the Sankey diagrams for the cost reflows. This figure shows how the air preheater output represents the highest cost. This cost was $1,779 per hour, followed by the flue gas output. This cost was $1,595 per hour. And the conclusion were number one, the entire system achieved as the thermal efficiency of the 71% and an energy efficiency of the 39%. It can be concluded that just over 60% of the biomass energy quality is lost during the processing, primarily in the combustion chamber. Number two, the exergy analysis revealed that the greatest exergy destruction occurs in the combustion chamber, followed by the biomass gasifier. The gas turbine and absorber show the best and the worst exergy performance respectively. And number three, the steam turbine had the highest capital cost, followed by the combustion chamber, air preheater, and air compressor. And number four, regarding energy efficiency, the gas turbine, air preheater, and air compressor had a high energy efficiency, while the ARC absorber had low efficiency. Thanks for your attention. This was the reference